8.4 Polar covalent bonds. Though atoms often form compounds by sharing electrons, the electrons are not always shared equally. Fluorine pulls harder on the electrons that it shares with hydrogen than hydrogen does. Therefore, the fluorine end of the molecule has more electron density than the hydrogen end. Electronegativity is the ability of atoms in a molecule to attract electrons to themselves. On the periodic table, electronegativity increases as you go from left to right across the row and from the bottom to the top of a column. Fluorine has the highest electronegativity on the periodic table. When two atoms share electrons unequally, a bond dipole results. The dipole moment produced by two equal but opposite charges separated by a distance r is calculated as follows. It is measured in a unit called debye. The greater the difference in electronegativity, the more polar is the bond. We can see in this chart that the greatest difference in electronegativity in the examples is between hydrogen and fluorine, 1.9 difference. Also, our dipole moment is 1.82. So this is the most polar bond out of the examples shown. In each case, which bond is more polar? Indicate in each case which atom has the partial negative charge. We are asked to determine relative bond polarities given nothing but the atoms involved in the bonds. Because we are not asked for quantitative answers, we can use the periodic table and our knowledge of electronegativity trends to answer the question. The chlorine atom is common to both bonds in A. We have boron to chlorine and carbon to chlorine. Therefore, the analysis is reduced to a comparison of the electronegativities of boron and carbon. Because boron is to the left of carbon in the periodic table, we predict that boron has the lower electronegativity. Chlorine, being on the right of the table, has a high electronegativity. The more polar bond will be the one between the atoms having the lowest electronegativity and the highest electronegativity. Consequently, the boron to chlorine bond is more polar. The chlorine atom carries the partial negative charge because it has a higher electronegativity. So once again, we're looking for the greatest difference in the electronegativity values. In example B, phosphorus is common to both bonds, and the analysis reduces to a comparison of the electronegativities of fluorine and chlorine. Because fluorine is above chlorine on the periodic table, it should be more electronegative and will form the more polar bond with phosphorus. The higher electronegativity of fluorine means that it will carry the partial negative charge. We can check our answers using figure 8.6 in our textbook. Practice exercise. Which of the following bonds is most polar? Sulfur to chlorine, sulfur to bromine, selenium to chlorine, or selenium to bromine. Sample exercise 8.5, dipole moments of diatomic molecules. The bond length in the HCl molecule is 1.27 angstroms. Calculate the dipole moment in debye that would result if the charges on the hydrogen and chlorine atoms were +1 and -1 respectively. The experimentally measured dipole moment of HCl is 1.08 debye. What magnitude of charge in units of E on the hydrogen and chlorine atoms would lead to this dipole moment? We are asked in A to calculate the dipole moment of HCl that would result if there were a full charge transferred from hydrogen to chlorine. We can use equation 811 to obtain this result. In B, we are given the actual dipole moment for the molecule and we'll use that value to calculate the actual partial charges on the hydrogen and chlorine atoms. Dipole moments are usually reported in debye's, a unit that equals 3.34 times 10 to the negative 30th coulomb meters. For molecules, we usually measure charge in units of the electronic charge, E, which is 1.60 times 10 to the negative 19th coulombs, and a distance in angstroms. This means that we need to convert units whenever we want to report a dipole moment in debye's. The charge on each atom is the electronic charge, 1.60 times 10 to the negative 19th coulombs. The separation is 1.27 angstroms. We're converting angstroms to meters, and then using 1 debye is equal to 3.34 times 10 to the negative 30th coulomb meters to get our final answer in debye's, which is 6.08. We know the value of mu to be 1.08 debye, or the dipole moment, and the value of R to be 1.27 angstroms. We want to calculate the value of Q, which is the charge. We can readily convert this charge to units of E. So if we rearrange the equation and say Q equals mu over R, we get 2.84 times 10 to the negative 20th coulombs. And then a simple conversion from coulombs to units of E is 0.178. This tells us that the experimental dipole moment indicates that the charge separation in the hydrogen chloride, or the HCl molecule, is plus 0.178 for hydrogen and minus 0.178 for chlorine. Because the experimental dipole moment is less than the calculated in part A, the charges on the atoms are much less than a full electronic charge. We would have anticipated this because the HCl bond is polar covalent rather than ionic. The dipole moment of chlorine monofluoride is 0.88 debye. The bond length of the molecule is 1.63 angstroms. Which atom is expected to have the partial negative charge, and what is the charge on that atom in units of E?